I'm going to have this presentation on out-of-phase switching of circuit breakers. Section 1, out-of-phase breaking, between opening the out-of-phase sources. In this case, the severe condition is when systems are out of steps. So we have loss of synchronism between two areas, and a circuit breaker between two areas is going to break the current and make the islanding to system. The magnitude of out-of-phase breaking current shall be below 25% of circuit breaker breaking current in accordance with IEC 62271.100. You're going to explain that later on. So a steady state condition before out of a step. In a steady state system, we are going to study, we have two areas, sys network areas, that we have a lot of generators and loads in one area and generation and loads in other area. So in a steady state condition, if this equation is positive, then the current will actually go through the positive, and this magnitude is negative. Is current flowing in this way, otherwise flowing this way. So from network point of view, we can have an equivalent source and impedance for the area 1 and source and impedance for area 2, which is the impedance is basically short circuit level of the area 1 at this point, and then Z2 is the short circuit, can be calculated from the short circuit level of area 2 at this point. So to calculating Z1 and Z2, we need to actually know the short circuit level in each side, and also X2R ratio of short circuit level, and also the voltage factor that been used to calculating short circuit level, especially when using the IEC 60909. So to knowing the wave equation, voltage wave equation of each area, we need to know the voltage of the area, the average voltage, and also the initial phase of the voltage at time 0. And also, which is not very important in terms of the different frequencies, because the different frequencies means time varying type of phase shift between two sources. But anyway, we need to know that, or one of the things we should put. But normally the role of these elements are mostly when we have a fixed frequency. And also the two frequencies, which is in two systems because of out of step and loss of synchronism. So basically in this case, we need to go to the time domain analysis, because when we have two different frequencies, we cannot use phasor diagram to solve this equation. So if we want to know the voltage here in time domain with two different frequencies, then we're going to the superposition theorem, that using putting zero value on this source and calculating the voltage from this source here, and then putting a zero value in this source and calculating voltage from this source, and then make summation of them. So basically these two voltages are based on superposition, and the final voltage is this one, which is what we see, that the initial value of the voltage plus the value of this ratio between impedances, which will add it to that. So this is the equation of voltage at this point. So, and then going to the current, we should actually select arbitrary direction for the current. For example, now we use this side to this side, and then again with superposition, we're putting zero value in here and calculating the current in this way, minus for the putting a zero value in this source and calculating current in this way, and then the summation will be two currents minus each other. So we see, and for both of them we have the phase angle phi equal to each other, which is the angle of, if I put minus here, then is the value of angle between angle of Z1 plus Z2. Okay. So, and then going to a steady state, we're going to just simply go to the steady state type of analysis, but is enough to understand the whole phenomena. When the circuit breaker contact is opening and traveling, the first point that the arc is extinguished, at the first point it still is traveling, basically the current will come to the zero. And a voltage will be generated between traveling contact and the fixed side. This voltage is important because, I mean, we need to know this voltage and the current that is being interrupted. Because normally the circuit breakers, in default condition, normally the voltage over the contact is the phase voltage, which is the line voltage divided by a square root of 3. Because normally when you're opening that, one side is no voltage, one side it has voltage. So in this case, and the breaking current of circuit breaker is based on that voltage, then they tell you that it's going to be for example, 50 Ka. Just 50 Ka is when they have this voltage over that. Otherwise, if this voltage is higher than the rating value, and its current is high, then because it's not been cooled down, the arc, still there is a chance when traveling to re-striking and reconnecting to circuit to each other, which is not good with breaking over voltages. And the over voltages cannot be studied by this circuit, simple RL circuit. But generally, we know that we shouldn't have re-striking. And the standard puts some criteria to minimize this incident. But anyway, when the arc is interrupted, then the voltage in this circuit analysis, the voltage over the circuit breaker is basically this voltage minus this voltage, because there is no current here. So we know that's a circuit breaker. When interrupting the current, then we have this voltage over the contact. Before going further, we're just backing to something a bit basic. A standard rating of a circuit breaker in a two-end fit system shall be greater than the greater short circuit level. Basically, we have a short circuit rating in this point, or any point, or this point, doesn't matter, which is basically if we have an equal R to X to R ratio of two sides, which is almost the case, then the short circuit of system is the short circuit from source 1 plus the short circuit from source 2. So if we have 35 Ka from this source and 25 Ka from this source and 60 Ka short circuit level, it's like this. Circuit breaker normally only see one of them. You cannot see both of them. The short circuit here is 60 Ka, but it either see 35 or either see 25. It cannot see both of them. So in case you know the minimum requirement in circuit breaker sizing is to be greater than the short circuit level of one side, which is the greatest. So we're just putting a quotation from IEC 62271.100. The rated out-of-phase breaking current shall be 25% of rated short-circuit breaking current of circuit breaker, and the rated out-of-phase making current, which is going to explain in this next section, shall be the crest value of the rated out-of-phase breaking current unless otherwise specified. So basically, short-circuit breaking current should be 25% of short-circuit breaking rating of the circuit breaker. So now we have this example here. So basically this side we have 25 Ka short circuit level from this side with 25 X to R ratio 1.1, basically equal to each other, and the Z be calculated, Z1, Z2. And basically the voltage here, 1 per unit, two sides. The only difference is the frequency of this side is 50 Hertz and the frequency of the other side is 51 Hertz. 1 Hertz difference. And the circuit breaker short circuit rating is 25 kA. The system is 275 kV. What have in the first, as we show how to calculating the VT, and you see that we explain here VT, how to calculating VT. Then we see that, okay, we have this wave. And it's very important to know that's a strong signature of out of phase. When you have some report from the relays and operated and some event recording and using this pattern of the wave, it means you have two frequencies in the system. And this value here, if you look at that, is a 1 second. So basically is the difference between two frequencies, 1 Hertz and 1 second, is going to repeat here. So that's why we have two frequencies in the system, and it's a strong signature, and very good to know that. I have seen many record, the event fault records from the relays that exactly have this sort of pattern. So this means there are two frequencies. And you see it's 1 per unit here, so that's the voltage when you have out of phase system. Then I bring the two other things. This is actually voltage of circuit breaker when the contact is open. Basically, this voltage, is E1, E2. This voltage minus this voltage. So you see that the pattern of that is it's going to reach to the 2 per unit, and then coming down, and when the voltage of, the RMS voltage of circuit breaker is almost zero, is maximum. If we open that at this point, I should expect to have a 2 per unit voltage over the contact. One thing. In terms of the current, you see it's same pattern of contact here, which means at the voltage of almost very low, the RMS voltage of the circuit breaker, we have the maximum current, which is it being normalized based on the circuit breaker short circuit rating, which is 25 kA, and it reached to the point almost 0.9 per unit. So it's almost the short circuit rating of the circuit breaker will pass at this point. So as I told before, this point is the worst point to circuit breaker interrupting the current. Why? Because as far as interrupting the current at this point, it has 2 per unit voltage over the contact, and it has maximum short circuit. It should interrupt the maximum current with the maximum voltage over the contact. So, indeed, the worst instance of opening circuit breaker voltage RMS minimum is just this point before opening 2 per unit voltage over the contact. And then the current will passing is almost 90% of short circuit rating of 25 kA. Then it's not compliance with IEC 6221.100, which should be 25% in this case. It is 90%. So we're going to the next, and we're increasing the circuit breaker short setting to 50 kA, basically the short circuit level of the system, not 25 kA. Still the same pattern. We see that the current is 45% now of rated 50 kA. Still is not complying. Then we selecting 85 kA. We just say 85 kA short circuit breaker rating, then it's complying is less than 20, it is almost 25%. So now we can say if this circuit breaker is supposed to interrupt out of phase current, and the worst point to interrupt is this point, then we should somehow increase the rating of short circuit breaking current of that special breaker if it's required to do this operation. So section 2 is out-of-phase closing or out-of-phase making current. It's different type of approach here. Out-of-phase making current shall be below peak value of the allowable out-of-phase breaking current. So if we have a allowable out-of-phase breaking current, which is 25% of short circuit breaker rating current, and the crest value of that, the making current should be less than this. This one is a bit interesting to analysis. Before that, why we need to make or connect two systems with the different phase, or not out, they are out of phase. So there are some operation scenarios, for example, auto-reclosing in EHV systems. In the power system, that a circuit breaker needs to close between two out-of-phase systems by using sync check relay. So basically, in normal condition, we have a power line between two areas. So we have a transient fault, lightning, and on the line. Then two breaker at the two side of line will open. So, and then reclosing the circuit breaker 1 on the dead line, which is no problem. But when you want to reclose the circuit breaker number 2, basically you are going to connect two systems which should be a bit normally out of phase to each other. So you're using a sync check relay and putting some allowable limit for the phase shift between two of them, and allowable the frequency. We're not going to explain, a study on that, and the voltage. So if the allowable phase shift is set, so what we can do is say, we're putting the very low value of this phase shift. We want to be safe. But the problem is, if you put very low value, then there is a risk that circuit breaker cannot be reclosed at all. You never reach to that point. If you said putting is 5 degree difference between these two is maximum allowable phase shift, then you never see 5 degree and this cannot be reclosed at all. But the too high value causes excessive over voltages, which is re-striking in the close-open scenario, an unstable power swing, loss of synchronism between these two areas. With a stable power swing, coordination between protection system and the stable power swing shall be in place for preventing maloperation of protection system during a stable power swing. Before that, I explained that just simply explain two sine wave with the theta degree phase shift. Let's say two side of breaker, we have two sine wave, just random sine wave. They have a phase shift to each other equal to the theta. So we can actually prove that at the theta divided by 2 point, we have a maximum difference between two phases. So if we actually minusing Vm sine omega t minus Vm sine omega t minus theta, which is the blue one, at theta point 2, theta divided by 2, we're reaching the maximum difference. So if you have 0, is increasing the difference between, and we have reaching to theta divided by 2. So basically, this random wave, they are 90 degree apart from each other. So we see that even is maximum, this is 0, so 90 degree different. It wants to say in 45 degree, we have the maximum difference between two. If they are 180 degree difference, so the other wave is like this, then at point of 90, theta divided by 2, we have the maximum differences. Here I just put the how to prove that in terms of mathematically. So if someone wants to look at that, is just the function is this function minus this function, and put the derivative equal to 0, and then we're reaching to the point that the omega t equal to theta divided by 2 make this one maximum. So this is very important, because normally when you're using this time domain software or transient softwares, they use many, switching in different times to calculate the worst point. But in this case, we know where is the worst point. The worst point is theta equal any phase shift between two. The worst point that we have maximum voltage over the circuit breaker is at this point, theta divided by 2. So one sort of playing mathematically with that is, say, instead of two waves, we're saying that one of them is omega t sine omega t, the orange one, and sine omega t minus theta, the blue one. Instead of putting like this and say at omega t equal to theta divided by 2, we have the maximum. We can moving vertical axis, we can moving this axis in this point and say that the orange one is omega t plus theta divided by 2, and the other one is omega t minus theta divided by 2. But the advantage of that is it is the worst case maximum at omega t equal to 0. So if we subtract these to each other in omega t equal to 0, we get the maximum difference here. So then we're going to worst case initial out of phase current at t equal to 0 for theta angle phase shift. Assume two side voltages are equal. So we're assuming the voltages are equal and they're putting the plus theta divided by 2 minus theta divided by 2. And that's the initial condition. It was to closing this breaker in two out of phase system, which have these voltages. When there is no current here, this voltage on here, and this voltage is here. But what is going to be in a steady state condition? In a steady state condition, it depends on, as we said before, in the generation minus load in each area, it could be either current going to do this way or that way. It depends on the delta angle. Is this one is positive and this one, positive than this one, or delta angle of this side is positive than this one, then the current will go to this way. So at t to infinity, subject to system stability to ride through transient power swing and maintain its synchronization, system load flow will determine the magnitude and direction of a steady state current and relative steady state delta angle. Just keep in mind, for a study on the circuit breaker making current, which is only first or second cycle of switching the breaker, we are not interested to see, we are not a steady state current together with time to reach a steady state current are not important. So basically, it's the steady state current to this phenomena. You need to do a stability study to see and putting all this generation and swing equation in place. But we don't need that. We only interested on very few cycle, even first or two cycle, with the current reaching to its absolute peak value. When circuit breaker closes on an out of phase voltage, it sees the peak current within first cycle, 20 milliseconds. For calculating out of phase, it should be OOP, making current, simple RL circuit is adequate for this analysis for first and second cycle after circuit breaker closing. What is the result of this discussion is we only study out of phase making current, and this circuit is enough for us for the first cycles. We assuming this going to go to these steady state values, which is not correct, but is valid for that few cycles at the beginning. So we have a very RL circuit that is going to close in t equal to 0, and they are the voltages in case, and then when we're expecting to for the current, again with the superpositions, whatever, we have a DC component and the final steady state, which are again emphasize that is not actual steady state, but it's kind of a steady state at the short circuit study of these two currents, which is this angle minus the angle of the whole summation of the impedances, and this is and then minusing each other, because this current minus this current is going to arbitrary direction. So initial condition in t equal to 0, it should be 0. So if we're putting t equals 0 in here, then the k factor being calculating is like this. We're not going to use that, but if you are interested how come we're reaching to from these mathematical equations, I put something here: sine A plus B, sine A cosine B, and that's the equations are used to prove that. And in the second part, the steady state part is this this part. This part we can say is kind of a vectors, two vectors, because now we have a constant frequency. So which one? I mean, we're taking the common part out. We can say is 1 with the degree of theta divided by 2 minus phi, and the other one minus the minus theta divided by 2 minus phi. And the result of this with the angle of 90 degree minus phi. So to prove that, basically we need to know that this is a vector with a angle is cosine A plus j sine A, and the other equations here cosine A plus B, I mean, and A minus B. You need this equation to actually prove that. And what is going to say that this part is equal, if we return that to the time domain, is like this, plus 90 degree minus phi sine 90 degree minus phi, which is a cosine omega t minus phi. So this value. Why is R important? So at the end, the current at t equals 0 is a DC component plus a component, a AC component, which is kind of a steady state. And you see there's an interesting part of that theta has some sort of impact on the value of the short circuit current. I mean, basically, this is a typical shape of short circuit current. This is not a short circuit current, but the phenomena looks like a short circuit current that we're expecting in typical RR circuit. We are expecting an AC value for constant short circuit level and a DC factor. So basically, the R to X, R is the summation of two R's, and X is summation of two X, and L is X divided 2 pi 50, and angle is X, meaning summation of them X divided by R. The maximum voltage here, what is the maximum voltage here, is basically is a square root of 2 of phase. This is a phase voltage multiplied by square root of 2. But if we're considering over voltage in the system, then this maximum voltage should have additional factor for including the over voltage in the system. So if we actually replacing this factor with the line voltages and other thing here, then and we're taking out a square root of 2 from this component, that's a typical pattern of short circuit current, but with the out of phase short circuit current of this one is equal to this. So it's kind of a short circuit which has some value on the angle, initial angle between two phases. So we can a bit simplify that. Normally, the X to R ratio if two areas are equal to each other. And when the X to R ratio of this side equal to X to R ratio of this side, Then the magnitude of the summation of Z1 plus Z2 is equal to magnitude of Z1 plus magnitude of Z2. And if we're dividing these two sides of equations by this value, 1.1 VLL divided by a square root of 3, and two sides of that, if dividing by this value, then we see that basically the inverse of this component, which is 1.1 VLL divided by Z1, is short circuit level from source 1. If you want to know short circuit level from source 1, basically is this one. And also the inverse of this one is the short circuit level from source 2. So this value now is equal to inverse of short circuit level of source 1 plus inverse of short circuit level of source 2. Then if we inverse two sides of these equations, then this value is equal to basically short multiplication of short circuit level of two sides plus summation. Then we back to the equation we found for out of phase short circuit type of current. I use the word of short circuit, but remember there is no short circuit. There is no fault. So is almost equal to 2 times of sine theta divided by 2 multiplied by 2 short circuit levels at the two sides divided by the summation of 2 short circuit levels. So it will give us what is the kind of current is going through this circuit. And you see if there is a zero angle, it's going to be zero current. So if it's a very low angle between them, there should be very small current. So it doesn't mean I use the word short circuit, but it depends on really what delta difference between the two sides. So it's a very famous equations. One thing, I don't want to draw that equation because now we have everything in this equation. We can draw it and find the peak value of that. But I want to keep in the standard type of approach and normally use the bit conservative equations. So there is a very famous equations when to calculating I peak from the short circuit. If you know the I short circuit, then multiply that by a square root of 2, multiply that by K factor. And the K factor is this equation actually the variation is x to r ratio. This equation is everywhere. It's just AS standard 3851, equation 8.19, or IEC 60909, equation 54. It's very famous equation. So basically, I peak is equal to the short circuit, AC short circuit current initial multiplied by the peak factor. And for out of phase current, then we calculating this as the I double prime, kind of I double prime. And this is the factor for K factor, and this is the square root of 2. So now we have the absolute peak value of out of phase current, making current. We return to the IEC standard to see what is criteria. The rated out of phase making current shall be the crest value of rated out of phase breaking current unless otherwise specified. What is the crest value of rated out of phase breaking current? The crest value of this, if the IBCB is the circuit breaker breaking current, the crest value in the conservative case, which is minimum crest value, is a square root of 2 of circuit breaker breaking current. Normally is equal, but normally we should use the breaking current. And we know that the allowable out of phase breaking current is 25% of this. So the peak value of out of phase, this one should be less than 25% square root of 2 the breaking current of the circuit breaker. There should be some sort of okay. So it should be this equation, and we just putting the peak value that we calculating should be less than this, then the maximum theta value, the sine theta divided by 2, should be less than these values. Now we're going to the example. A circuit breaker with a breaking current of 35 kA is between two systems with 35 kA and 25 kA short circuit level. So basically we have two systems 35 and 25, and I said, as we said before, the circuit breaker should be minimum equal to the biggest of this, so it's 35 kA. The XOR ratio at both sides is 25, basically both sides, and the summation is the same. What is the maximum angle can be set in sync chain relay to comply with the standard? So with this value here, we basically have 35 kA short circuit from breaker, and 35 plus 25, 35 multiply 25, and then, sorry, it's been an E missing here, E minus, yeah, oh, okay, E minus here. It should be less than this value, and this means that the theta divided by 2 less than this, and the theta less than 18 degree, almost. So it means up to 18 degree. I mean, if I just put in engineering practice, let's say 20% contingency, let's say 14.5 degrees. So that's the maximum delta angle between two sides. The circuit breaker can close in this angle. Even the worst point, it cannot reach to the 25% of circuit breaker current. Why is it's important? So somebody may say, okay, we want to close the breaker. We don't care about should be low current. Because normally in the circuit breaker type of approach, we expect close open. So something close and very quickly after that, for some reason, protection operation or whatever, the circuit breaker close and open. It's still not stable, and when it's opening, basically opening a two out of phase circuit is still in turbulence. In this case, it should actually follow whatever the breaking current is. That's why the breaking current is come into place. But before closing this presentation, I need to say that this practice been done for circuit breaker just looking at IEC 62271.100 requirement for circuit breaker. It doesn't mean that if you put 14 degree here, for example, everything good. It's good for a circuit breaker doesn't have a stress and can basically not stressing, not bringing excessive overvoltage in the system for close open operation. But you should keep in mind that out of phase closing may cause either a stable or unstable power swing. So we're expecting to have some sort of power swing, because if this one is positive from this one, the angles, definitely the current are initially going from this way, the power. But it doesn't mean at the steady state final condition, the power of this side is more than the power of this side. And a steady state condition, the power would be from this side to this side. So definitely we have power swing. And this angle is much huge, much bigger than the steady state angle, which expecting from delta angle for power swing. For example, let's say this one is 14 degree. Let's say 14 degree, as we calculated, is 14 divided by 2, or 7 degree here and 7. So they have a 14 degree difference between two sides, but in the delta angle, maybe 2 degrees. So that means at the beginning is definitely with this equation coming from that way, but it's the power swing is dictates something else. So definitely we have some sort of power swing. Either is a stable power swing or unstable power swing. Separate study shall be in place for system analysis of power swing. So the power swing, so we're putting the 14.5 degree, for example, the phase angle between two in the software studies or whatever we have, and we are studying that if we have a stable power swing or not. But even with a stable power swing, it doesn't mean everything good. Because in the stable power swing, the calculated value of allowable phase shift could be checked if it will not create protection maloperation, especially in distance relay. So in distance relay. So we just say we have a distance relay. Let's say if have this zone. So what it sees that the power swing is reduce of the impedance, and if it's a stable power swing in and out, then if it has a power swing blocking, then it understands that. But sometimes it doesn't have power swing blocking. It sees it as a fault, so it will operate it. And then the other thing is about and also overcurrent relay. It sees that as maybe a fault. So this sort of a study should be in place. For example, some other protections like line differential is stable about this because it doesn't see power swing or anything that, because it just sees the two currents from two sides. So, but yeah, that's at the end. I want to say it's a bit complicated topic, but with this approach, you really may understand why the IEC using this sort of criteria for out of phase switching. I hope it worked for you, and you'll be and next time we have other presentation in place. Have a good time. Thank you. Bye.